Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about another important family of probability distributions, the gamma distributions. My plan for this video is first, I'm going to show you the expression that defines the PDF of a random variable with a gamma distribution with parameters alpha and beta, and then we will derive together the formula to quickly find the expected value of a random variable with a gamma distribution. Okay, let's begin. So the first item in our agenda, showing you the definition of a random variable with a gamma distribution. That's what that guy looks like. Okay, so the PDF is going to be y to the alpha minus 1 divided by beta to the power of alpha times the gamma function. Remember the gamma function? We talked about it in another video. The gamma function evaluated at alpha, but now we know that, it looks kind of scary, but the gamma function evaluated at alpha will be just a number. So that is just a constant that is going to help this expression to be a legit PDF, meaning in this case the integral from 0 to infinity of this expression here will be 1. Okay, so as I said, this is the expression of the PDF in the part that is non-zero. Okay, because if you are if you evaluate it in negative real number, then that's going to be 0. So the non-zero part, the important part, is this: y to the alpha minus 1 divided by beta to the alpha times gamma evaluated at alpha e to the negative y divided by beta. Now, before we keep going, okay, so yeah, I already mentioned that we are familiar with this guy, the gamma function, and this is a reminder of how you define the gamma function. But let me say something more. You have already dealt with a gamma distribution without knowing it. Note that this guy has two parameters, alpha and beta. Okay? If alpha equals 1, then you have y to the power 1 minus 1, that's y to the 0 power, so that's just a 1. And then we know that gamma evaluated at 1 is just 1. And this is beta to the power 1, so it's just beta. So a gamma distribution evaluated at alpha equal to 1 is just 1 over beta e to the negative y divided by beta, meaning it turns into an exponential random variable. So you have dealt with a gamma distribution before. An exponential distribution, or a random variable with an exponential distribution and parameter beta, is a member of that family. Okay, so this is just a more general version of the exponential distribution. Okay, this is a wider family. Okay, so let's keep going. Now, that's a graphical representation of several members of the gamma distribution family. For instance, the one in red, the curve in red, is just when alpha equals 1, we know we have an exponential, and if beta equals 1, it's just e to the negative y. So, okay, makes sense. So this is another one when alpha equals 2 and beta equals 1, that's the blue one. The black one when alpha equals 4, beta equals 1. Okay, that we have dealt with that guy before in another video. In a separate video we introduced the gamma function, and we actually showed this, and we have also shown that property. Okay, we also mentioned that fact that when you evaluate the gamma function at an integer n, that is the same as computing n minus 1 factorial. Okay, so we have done that. I have shown you the definition of a gamma function, and we said that that's why we needed to talk about gamma functions, to be able to talk about the gamma distributions. Okay? Okay. We did this together, right? That's how we showed this property, integrating by parts. Okay? Now, this is the part that I would like to do with you together in this video. Okay, this is the part where we're going to be doing a little bit of math together. Okay, so anyway, we would like to have a formula to quickly find the expected value of a random variable with a gamma distribution with parameters alpha and beta. Okay, so it turns out that the expected value is just going to be alpha times beta, and the variance of a gamma distribution with parameters alpha and beta is going to be alpha times beta square. We are going to be doing this one together, and you can try and do that one on your own later. Okay? Okay, so let's find the expected value for random variable with a gamma distribution and parameters alpha and beta. Okay? Proof. So basically, by definition, in the case of a continuous random variable like the one we're dealing with here, the expected value of y is just going to be the integral from negative infinity to infinity of y times the PDF dy. Right? Agreed? No problem, right? We've done that before. That's kind of the generic formula. But now we know that we have to plug in, we have to substitute the PDF in this particular case. So we know that the PDF, if you are on the left hand side of the real line, if you have a negative number, so from negative infinity to 0, the PDF will be 0. So that integral will disappear. And then we need the other part, right? That's going to be the interesting part, where the PDF is non-zero. And in this case, we know that it looks a bit tricky, right? The expression of the PDF for a random variable with a gamma distribution. Okay, so it looks something like this. So y to the alpha minus 1 divided by beta to the power alpha times the gamma function evaluated at alpha. Okay, that's just one part. The other part is the one with the exponential e to the negative y divided by beta. Okay, agreed? Yeah? Okay. So the second integral is the one that matters. So let me just copy paste that one here, and we're going to see if there's something that we can do here to simplify that expression. So first, what if we do this multiplication? Y times y to the alpha minus 1. What if we rewrite that like this? Right? It's the same. Oops. Okay, that's better. So y times y to the alpha minus 1 is the same as y to the alpha plus 1 minus 1, right? No problem. Now, let me try and simplify this a bit more, right? We know that these are just constants, right? Gamma evaluated at alpha will be a number, beta to the alpha. Those are given, are numbers, so we get to factor those out. That is going to help us, I believe. So let's do that first. So it's going to be 1 over, let me copy paste just that guy there. Then I need an integral from 0 to infinity. 0, infinity. Okay. Okay, let me copy paste that part. And there's one too, right? We're going to need it. And we need that one too. Okay. So again, what I did there was just I pulled out that constant, okay? Now, take a look at the expression that is inside that integral. Take a good look at it. So now let me go back to the definition of the gamma distribution. Okay, let's have it here. There we are. So instead of an alpha, we have alpha plus 1. Remember, because we had to multiply by that y. And here we don't have a constant. But if we had a constant that looked like this with the right numbers, then if you integrate a gamma distribution from, well, if you integrate the PDF of a random variable with a gamma distribution from 0 to infinity, right, you know that it's a legit PDF. So the integral from 0 to infinity of something like this must be 1, right? So what we're going to try and do is a very, very popular trick among statisticians. Okay, so what we do is we complete the expression of something that we know is a legit PDF, right? And then we know that that integral is going to be 1, and that's it. So let's try and do that, okay? So we need y to the something minus 1, beta to the something, and gamma evaluated to the something. Okay, e to the negative y divided by beta. Okay, so let's see. The beta we already have. This one, e to the negative y divided by beta. We don't need to make any changes here. But here we need to divide by beta to the something. The something is alpha plus 1 times the gamma function evaluated at the something. The something is alpha plus 1. Okay, so that's exactly what we're going to be doing. We're going to divide by the constant that would make this expression inside that integral a gamma. Okay, so let me do it like this, right? This is 1 over beta and the power that I need is alpha plus 1. So let me write that down. Alpha plus 1, and I need to multiply by gamma, the gamma function evaluated at alpha plus 1 as well, right? Oh, let me borrow this one here. Okay, that's better. Alpha plus 1. Nice. But then you go, okay, yeah, that's a constant, no problem. But if you're dividing by that guy, then we have to multiply by that guy. And if we do that, we're just multiplying by a 1. That's a very kind of ugly one, but it's a 1. So we're not doing nothing, we're not doing anything illegal, right? But now when you take a look at this guy inside the integral, this guy here is the PDF of a gamma distribution with parameters alpha plus 1 and beta, and this integral will be 1. Make sense? So now what we have is this times kind of a nasty looking integral, but since we're integrating gamma with parameters alpha plus 1 and beta over 0 to infinity, that's just a 1, because that's a legit probability distribution. And we're done there. And now remember that property that we showed, that gamma evaluated at alpha equals alpha minus 1 times gamma at alpha minus 1, right? So now we get to use that property. So that means that this guy here, let me copy paste that guy, is going to be just alpha, right? Because the property, let me show you the property that we showed together. Instead of alpha, we have alpha plus 1, right? So gamma at alpha plus 1 is going to be alpha plus 1 minus 1, that's alpha. Alpha plus 1 minus 1, that's alpha. So that's just going to be alpha times gamma at alpha. That equals gamma at alpha plus 1. Okay? So let's do that. This is going to be alpha times gamma at alpha, right? But then these will cancel out, right? We're going to have alpha times beta, right? Because this is just, let me rewrite it like this. This is the same as, let me get rid of the 1 here, and let me just write another beta. Okay, so these cancel out, and we end up with just a beautiful alpha times beta. Okay, so that's the expected value of a random variable with a gamma distribution and parameters alpha and beta. Okay, so let's summarize what we did in this video. We introduced a new class, a new family of distributions, right? The gamma distribution family. This kind of distributions has two parameters, alpha and beta. we derived the formula for the expected value. It happens to be just alpha times beta, and it was useful for us to talk about the gamma function previously, so we could use some of its properties. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.